Hi guys, I'm Gautaman Asokan. I'm a AI researcher in Silsat, and the topic that we'll be seeing today is diffusers. So this is a Hugging Face library. So we will be briefly looking upon what is diffusion, what is stable diffusion, how to use the diffusers library, and we will also see the model architecture and some code samples of how to generate the images. And as you can see in this slide itself, like stable diffusion, DALI 2, Midjourney, everything uses the underlying diffusion architecture to generate the images. So we'll be seeing how it works. Uh, I'll be going to each slide explaining the concept. If you guys have any doubt, feel free to ask the questions in that slide. So what is diffusion? So diffusion essentially is taking some training data. These are some images that we take. You can see human face here, and iteratively we add Gaussian noise to it. So we sample a noise from a Gaussian distribution and add uh, to its iteratively. So you can see from x naught to xt, we add noise iteratively to make it a completely noise uh, noised result. So here again, so this is the forward diffusion process. So next, what we'll be doing is we'll be taking this noised image, and we will be trying to reverse the diffusion process. So here, if you see, we are going from in the forward diffusion, we are going from x naught to xt. So in the backward diffusion and the reverse diffusion, we will be going from xt to x naught. So we'll be going successively to get this original image. So this is essentially what the diffusion process is all about, and this is one of the sampling methods. So here we will be seeing how what are the different ways in which images could be generated. The first is generative adversarial networks, where we have two competitive networks called the discriminator and generator, which will the discriminator will try to detect the real images, and generator will try to sample images so that they feel like real images. So this um, cross training between these two networks produces images. So this is how the generative adversarial network works. Again, there's other different models like variational autoencoders, where you have the image and there's an encoder which compresses the image to a lower latent space, and from this lower latent space, again the decoder uh, tries to bring back the original image. So this is a variational autoencoder. There is also models like flow-based models, where you just find a function with which the X space becomes the Z space, and again from this to the original images space. So this is the flow-based networks, and this is the thing that we are seeing today. The last one, which is the diffusion models. So in the diffusion models, what we do is we successively add noise and try to reverse it to get the images. So these are the different ways in which we can be training the models to generate images. So these are the different generated models, and essentially what they are trying to do is they're trying to model the data distribution. So what is the data distribution looks like, and the model learns that data distribution. Once it learns it, we can sample some point from the data distribution and try to generate images. So this is the basic underlying idea behind different generative models, and diffusion model is one such thing.
So there were some questions already. One question was actually from my side. So is diffusion model state of the art among all these four?
Yes. As of now, it like 2-3 years back, generative adversarial networks was a very state of the art model, but once the OpenAI actually introduced diffusion to their DALI networks, and from there it caught upon. And now, whatever is see the AI images, it's mostly focused on diffusion model.
Next question on the chat is, what is the intuition of adding noise? Why add noise to regenerate the original?
So noise, essentially because they are altogether making it into a different network where it's completely noise, and from noise they're able to generate the images. So whatever the data distribution is there, they're altogether making it as a noise. From noise, it's able to do. The main idea is the success iterative steps. So from this, it's not able to do this. It's like successively and trying to uncover what is the actual image. So here, if you see, it's just a different data space altogether, but it's doing iteratively to get those images. So this is one thing that's helping to produce some high resolution images.
So basically, it's a trick that you take an original image, you add a noise, you corrupt the image deliberately, right? And
Yeah,
then you recover the image from noisy image, from the corrupted image. So in this process, it learns the art of producing similar new images, right? So it is an engineering hack or trick to progressively add more noise through neural layers so that the image is totally corrupted with noise. And then when trying to recover it, it will learn how to create similar images, right? That's the intuition, Gautaman. Am I right?
yeah.
Okay,
And also the distribution, they are trying to learn by neural networks. So diffusion has been around for a long time,
right.
but here if you see the p theta here, because it's learning, trying to learn from neural networks. I'll discuss on this more later. So yeah, so this is the comparison with other models, uh, and we'll be seeing how the diffusion works. So we'll be seeing the basic flow of how the diffusion works. What are the different components involved? The first thing that is involved is the unit architecture. So unit architecture is essentially looks like an autoencoder where there is a compression and there is a expansion uh, happening. So this is what it is telling also. There's a constructing part where the data is compressed, and there's an expanding path where it expands back to the original dimension. So what is the major difference between the unit and autoencoders is it uses this skip connection. So here you can see some skip connections where which allows the gradients to flow. So which makes the network even more optimized. And this is architecture that will be used in diffusion. So how it will be used, I'll be telling the upcoming slides and with the code example too. So unit architecture is what is being used in the diffusion process. And you take the basic unit, and what they have done is they have made certain changes in that unit architecture specifically for the diffusion process. So what are the things they have done is the first is group normalization. So there are different normalizations that we can be doing, like batch normalization, layer normalization, instance normalization, group normalization. Batch normalization is like you normalize across the whole batch. Layer normalization is like you normalize across a certain future. And here, if you see the group normalization, even across the channels, it's just a particular set of group, just a group is being taken and normalized. So this kind of a group normalization, where it divides the channels and normalize the features. This is something that has been working in the diffusion. So they have been doing this. group normalization, and they have also this dropout layers for the smoother training. And the other important thing is this attention and conditioning on the time step. So how they do that is, so here you can see the how the modification is being done. So this is the time step. So what is the time step? The time step is like they try to uh, add the noise iteratively, right? Like the first step is the noise amount. Let's take the first step as 1, the second as 2, 3. So this is the conditioning on the time step. So even in the reverse diffusion process, we explicitly tell what is this time step. So that helps in predicting the image. So that is what uh, one of the modifications. So here, if you see this noise amount is 3, so it is telling that there is 3 levels of iteratively noising that has happened. So that is the conditioning on the time step that we are talking about. And the next thing is the text information. So the text conditioning is something why we use this, of course, because we write the prompts and we try to generate images with the help of that. So how that is being uh, uh, integrated into this architecture is like we have this text information, and this text information goes to these different layers, attention layers, and this noised image, uh, once it goes to the ResNet, it comes to this output path, and from this attention layer works so that it understands which paths to be generated in which way according to the text information. So let's take, for example, a man is standing on the top of the building. So this is the image that we try to generate. So how the text information is helping is it essentially tells how the spatial configuration of each thing should be. So there should be a building that is being generated and the person on top. So the person should be on the top. So these kind of the spatial information is being learned by the model with this text conditioning, and that is being achieved through this attention module. So these are the different unit modifications that we do in the diffusion process. We're also,
I have one
yeah.
question.
Oh, yeah.
Sorry to interrupt. So actually, the model is predicting the noise at every sample, right?
Ah, yeah.
But what are the? I mean, if the text information, how are we ensuring that we are getting the image corresponding to the text? What are the losses being used here?
I'll tell like loss here. The unit essentially is like the input is the noise sample, and the prediction is the actual image. So that is the basic unit idea. Based on our certain inputs, we will be able to integrate other losses also. I'll be explaining something like there is other parameter called guidance. So we'll be
Mhm.
also seeing through that. But the basic architecture is like giving a noise image and getting a clean image. So the clean image, so what is the output and the clean image? With these two, the mean square error is what we'll be computing for the basic unit model.
Yeah, but the mean square error is for the predicted noise and the actual noise added, right?
Ah, yes, yeah.
But then my question is like, see, when we are using the text conditioning with just the RMSE over the predicted noise and the actual noise, so how are we ensuring that we are actually seeing an image conditioned on the text? Because there is no explicit in the architecture. Actually, there is no explicit. I mean, condition the attention we are adding, but that's an input. But in the feedback process, we are not getting anywhere. I mean, these additional information that this image is not related to the text condition. So
Ah,
how
yeah.
are we ensuring that?
So for the so that is a particular conditioning, and for that people use different losses like clip loss they use. So what is clip loss and how they use it, I'll tell in the afternoon.
Okay, sure. Thank you.
So these are the unit modifications. So if you're clear, we can go to the next thing, which is schedulers. So the main two things in the diffusion processes, one is the unit that we saw, and second is the schedulers. So these are components that is used along with the unit. They play key role in denoising, noising and denoising both. So what schedulers will be doing is at different time steps, they'll be telling how to add the noise. So these noise could be added in different ways, and there are different schedulers which add noise in different ways. We'll be particularly looking at one famous scheduler, which is the DDPM scheduler, which is the denoising diffusion probabilistic models scheduler. So we'll be seeing how it works, and we'll also see in the code sample how the scheduler is being used. And here you can see, so this is the plot of the DDM scheduler being used. And so the DDM scheduler, if you see this orange, this is the noise being added. So you can already see that the noise being added saturates to 1 quickly. And this is the clean image. So that how much portion it should be there. So that is this blue line, and there are different ways in which the noise could be added. So DDPM is one such way. So how it is being added, how this scheduler works is, we have this noise, which is this epsilon, and we have this parameter, the diffusion parameter, and we try to, in the forward diffusion process, essentially what we do is, we try to add noise iteratively, right? So this is a noise, and we have this diffusion parameter, and we are scaling the actual image by this diffusion parameter and the noise by this diffusion parameter to get the noise sample. So, and this noise is being taken from a normal distribution, 0 to I. So once we have this epsilon, which is the noise, we iteratively sample it and try to noise the image iteratively. So this is the thing. And other important thing to note here is, so here what happens is, we will be iteratively noising the image, right? There will be a clean image, and we will be going to x1, x2, x3 to the xt. Let's take, for example, there is a xt. So for the final completely noised image. But here, let's take, for example, there is 1,000 steps or 10,000 steps. To noise it iteratively to that 1,000 step or 10,000 step is a tedious task, and we can get around this thing with a thing where instead of going from x0 to xt, we can go from directly to x0 to xt by this additive property. So what they have been doing is, they are initializing this 1 minus beta as alpha, and they are adding those. So let's take, for example, there is x0, xt, x1, x2, xt, right? So they multiply all those parameters to get this alpha, and with this they are noising the image. So instead of going from x0 to x1, x1 to x2, they are directly going from x0 to x3, xt by this method. So this is how they are doing in the DDPM scheduler.
So yeah, there are some questions. I think folks, you can speak up or ask or put your question in chat. There are some questions on chat, Gautaman.
Yeah. Does the structure of the image change amid the process of adding and removing Gaussian noise? And if it does, do we retain the structure or we do? Structure of the image change. No, structure of the image actually doesn't change while adding and removing noise. We determine how much the noise should be added. Once that has been added, the unit architecture, there the structure is like what I have showed. It contacts expense again back to the original dimension. So that is the thing. So hope that is the thing that you are asking. Is it clear?
Yeah, basically it is able to recover the original image, so it maintains the structure, right? So it remembers the original structure, only noise has been added, and using Gaussian noise, so it predicts how much noise to add using the Gaussian probability distribution model for the noise generation itself. So now one question, Gautam, and I wanted to ask was, what is the intuition of using Gaussian noise and not any other kind of noise, if there is any specific reason for that?
Gaussian noise because
I mean, I guess they wanted to add controlled noise, right? So they found Gaussian noise works best, maybe.
Yes, yeah. Even that controlling, they do a lot, like the 0 to I. So this is a not a particular, it's a particular Gaussian. It's an isotropic Gaussian where again it's like a little bit more max where it's multivariate Gaussian distribution where they're trying to make it as a like the covariances variance into identity matrix. So in this way, that variance would be only aligned to axis. So they are making it even more aligned.
Right.
So that's about the forward diffusion process. The main things to understand is like it's taking the image from the previous iteration and the noise, and there is some diffusion rate that is being added to get the noise sample, and this could be done iteratively, and also it can skip to the particular time step. So these are the things that we need to understand the forward diffusion process. The next thing is the backward diffusion process. So the backward diffusion process, what happens is now we have the completely noised image, and we try to bring it back to the original image. So how do we do that? Do it is predict the parameters for the reverse diffusion kernel at each time step. So here, so it's essentially integration because like let's take for example the t to 0. It would be a iteratively we are doing to get back to 0. So that is the integral part. The main thing to understand the backward diffusion process is, let's take for example we have this xt and we try to determine what this xt minus 1 image is. So for that we are trying to model a distribution where we are trying to find the mean and covariance with, and this mean and covariance is being modeled with the help of a neural network where the input parameters are this particular noised image and what is the time step. So this is the time conditioning. So with this time conditioning and this noised image, we try to model the distribution of how it would look like. So this is what is the key factor here. So we try to model the distribution which needs the mean and the covariance, and this two are determined with the help of the neural network. So this is what the thing to be remembered in the backward diffusion process. So we see here how the whole DDPM scheduler works. So we take this image and we try to successfully noise it. So here you can see the noise, it follows a distribution, and from this distribution we try to noise it, and once it's completely be noise, it looks like this. From this we try to reverse diffusion to go back to the original image. So here too it follows a distribution, and this distribution, what is the mean and the covariance, we try to find it with the help of a neural network. So this neural network uh, is the thing with which we model the distribution. From that, we will be able to find the denoising process iteratively to go back to the original image. So this is the basically how the DDPM scheduler works.
So some more questions. Let me just repeat them for you. What kind of applications can be created with this technology?
Diffusion process. So the recently the AI images that we see, we give different prompts and generate images, right? So be it whatever the underlying architecture, it essentially uses the diffusion process.
Right, pretty much all kinds of image generation in AI is now using, these stable diffusion DALI 2, which are state of the art. Now, another question is what level of proficiency of maths is required because the maths looks difficult.
Yeah. Even this scheduler that I'm discussing about is just one particular scheduler. There are like lot of schedulers, like even the most common ones becomes 20, 30s, and everything have deep mathematics in it. But like I'll be showing the code sample where you just need to initialize the scheduler. The basic idea, it will be good if you know it, but uh, beyond that, the scheduler part, you don't need to know much on the mathematics, but the diffusion part, you definitely need to know how it works.
See, I would like to augment this question because this often comes up. How much maths is needed for becoming a top AI scientist, right? So, because we have been teaching AI to tens of thousands of people over the last 5 years. So, what we find is there are two levels of AI scientists. One is somebody who is able to do deep research-based AI development. So, they are the maths. We have to go back to our high school and engineering college level maths skills. But many AI scientists are able to work without maths because they are ready-made libraries, right, in Python, PyTorch, TensorFlow, and other now new generative AI, GPT, or Stable Diffusion, DALI. So a lot of AI scientists are able to get away without delving into maths. But indeed, if you want to do slightly more sophisticated work, deep dive, intense product innovation, then math skills, you'll have to go back to your engineering level maths, or at least I would say 12th grade maths would be needed. At the end of the day, it is simple probability and union and intersection and probability distribution. So it's not that bad really. It's really what we studied in 10th grade, 11th, 12th grade. But if you want to avoid that, it's possible with ready-made libraries. So two kinds of AI scientists are possible. I hope that helps that question. Next question in the chat is, we are generating same image which was given an input. So how does it create totally new image, Gautam?
So this is the training process. So once the training has been completed, so it understands the whole distribution of the data. So it has learned the distribution. Now, if you sample a particular random point from it, it will be creating the new image because it has understood how the distribution works.
Gautam, and one, I don't know, uh, from my understanding, we will never be able to create a same image, right? Even in the training process, we will never be able to create the same image because we are adding noise at every pixel. And I mean, even if we remove the noise at that pixel level, even during the training, we will never be able to create we will just learn the distribution of the training data set, but we will never be able to create the same image.
Yeah. So the
Yeah.
objective is like to as far as possible to go to the original image, but yeah, even during training it will be difficult.
Yes. Yeah.
Yeah. So if those are the questions, I'll just show a code demo of how these work before going to stable diffusion.
So by learning this, it would be able to create new flower images only, or any type of image. So it has learned the flower image creation. That's what you're saying, right?
Yes. So it just depends upon the data set, right? Like you just in this
So
particular
set
example,
hundreds
yeah.
of images, you will train it using hundreds of images, and it will learn each and every image by adding a noise. Okay.
Yeah. So here we will be just going to what is the basic concepts that we have seen up to now, and how that different architectures is being used. The first thing is like we will be using the Hugging Face library diffusers, with which we can generate the images. We import the libraries that we need. The code we'll be needing is like what we'll be using to train is this MNIS data set where we have this handwritten digits, right? So that will be the images that will be used for training the diffusion process. So we have that data loader with which we load the data. We just see how it is. The input shape is like eight batch of 8 images with 28 cross 28 pixels, and we see what are the labels 1973. So as that, so this is the data that is being used for this particular diffusion process. The second thing that we'll be using is the corruption process. So how do we noise it? So I have told about DDPM scheduler, but here we'll be going to a very basic noising idea where we just first of all have what we'll be doing is we'll be creating a noise. So this noise needs to have a same dimension as our original image, which is the 28 cross 28 image of the handwritten digit. So once we create the noise, we will add the both the noise in the clean image, and we'll also be specifying the amount of the noise to be present and the clean image to be present. For example, if we just tell the amount to be 0.6, so the actual image would be 0.4, the noise would be 0.6. So in this way, both will be added to corrupt the image. So here we can be seeing how the corrupted data is. So we have the input data, and this is the corrupted data. So as we give more and more weightage to the noise, so here the weightage is 0. So as we add more and more weightage to the noise, here we can see that it's been completely corrupted. So this is the idea behind the corruption process. And we are taking the unit model. So unit model, we are just constructing. So as I said, it has some down layers where it tries to compress the whole image, and there are some up layers where it tries to expand it back to the original dimension. And here you can see that there is the skip connections that I told. So they are trying to do that skip connection in the forward process. So this is the basic unit model they have used. They're just taking like with the input sample, what is the output given. As I said, it's a unit. So whatever input you give, the output would also be of the same dimension. They are also seeing how much parameters this model has. It has about some 3 lakh parameters. So how do we? So now we have this data set of this MNIS. We have constructed this unit. So the next thing that we'll be doing is training this network. How do we train this network? Is so we load the data, we create the network, and then our loss essentially is this mean square error loss, and we specify the optimizer as Adam. And what we'll be doing is we'll be getting some images, we'll be corrupting that images, and once we corrupt those images, we'll be trying to predict the output, and this prediction with the actual image, we try to compute the loss and we update the network according to that, and we also try to plot and see how it looks. So here you can see that it has been stabilized, and we try to see how it is. So here this is the input image. So these are the different corrupted data that we have given, and the network is trying to produce what is the actual image. So here you can see when the corruption is very low, it's able to make some very good prediction, and when the corruption is very higher, it's not able to as such. So here you can see it's not able to as such predict those very good. So this is the problem. And for this, what they are doing is they are using the sampling process. So what is the sampling process is? This is the thing that where we do it iteratively. Instead of doing it just once, they're doing it iteratively to get back to the original image. So here if you see, so we have the sampling steps, we have told it as 5. So once we have told it as 5, what it does is it iteratively goes to 5 times, and it tries to predict what is the prediction. And this prediction is being used, so there is a mix factor. So this prediction plus the noise is being added in this same way as the corruption to get the denoising images. So this sampling process helps to get better images. So here you can see that this is the model, this is the model prediction. So again, this and this has been added to get this, and this has been added to get this. This way the sampling process works to get these images. So here you can see that this is a lot better than what we had initially. So that is a particular reason why this sampling process, this the iterative process being used in the diffusion. So these are some of the images that is being produced. So this is a simple model, so that's why there's no high resolution images being used. So yeah, so this is the basic idea of how the diffusers work. We saw about the data set, we saw about the unit architecture, we saw about how do we noise the images, we also saw about the sampling process to get the actual image. So once we are clear on this, instead of this basic unit architecture, now we will be using the unit 2D model. So a unit 2D model is something that what I have told previously. What are the different architecture changes that they are making? Like for example, they are using this group normalization, time step conditioning, attention. So these different things they integrate to get the modified unit architecture. So that is the architecture that is being used here. So here you can see that it has about some 17 lakh parameters. So the basic model has just 3 lakh, but now it has become 70 lakh parameter model, and it works better than that. Again, we have just modified the unit architecture. Otherwise, our loss, optimizer, training loop, everything remains the same. And here you can see that the generated samples are much better than the original basic unit architecture.
So there was a question: the what is the Y label, the target label? Is it the correct image? Or
Yes. So we have the clean image, we noise it. So noise is the input. The target is the clean image.
Okay, so it is supervised machine learning, right, Gautaman?
Yes, yeah.
Okay. It is not self-supervised, semi-supervised, it's fully supervised because the Y label is clearly present, right?
Yes, yeah.
So in GPT, it is semi-supervised. Yeah, go ahead, Arun, sorry.
Yeah, Gautam, like we are giving like corrupted input actually, and after that we just inferencing that one as an correct one. I mean the numbers are finding out. What's happening here actually, or am I wrong or right?
The corrupted image we are giving, it essentially the unit what we are trying to do is we are trying to make it learn to denoise it. So essentially, with the corruption, it will look like very noised, right?
Okay,
We are
you
trying to
mean
make
like
it denoise.
corrupted inputs are given and denoising it. After denoising it, it just giving the predicted result actually.
Yes.
Yeah. So you are saying that the denoising thing is which one? That is a unit you are saying.
Denoising the thing is a unit model.
Okay. The unit architecture thing. Yeah.
Yeah.
So where are this what are the applications mainly? Just for only the text prediction and image? Other than that, actually anything?
Diffusers essentially is for images. So the image
Oh, only for image.
generative images. Yeah. It can be used for text,
Okay.
but yeah, the images is what it's predominantly used.
Okay.
I mean, in future, all
you.
images, videos, graphics, everything is being done with Gen AI, right? So this is Gen AI for images. So the future is very interesting.
Okay.
There are all kinds of text, image, videos, movies, advertisements. Shah Rukh Khan is able to speak multiple languages, right? It is all generative computer vision. So it is very exciting
Okay.
future. Yes.
No, like yeah, like how you are like saying that one actually. We are giving a noise means that is someone else, something else. I mean, someone else, and we are generating some other things for that format. What's here noise actually?
Noise is it's a different distribution. So that is basically a complete different noise, right? What here we are trying to do is we are trying to map that noise to the whole this data distribution, the training data distribution, so that we can take some point from that noise and create images. So that is the idea. Here, whatever I am discussing is the like basic underlying architecture of how it works. So that I'll be telling about other modification that has been done to actually generate.
Okay. Yeah. Yeah, you can go on. Like, go on.
Yes, yes. So now we have seen how this modified unit architecture works. The next thing is the corruption process. As I told, the unit DDPM scheduler. So that is the now up to now the corruption process we just give amount of noising to be produced and we just add that noising levels between the clean image and the noise to get the little bit of that noised image. So here, instead of that, we use this scheduler. So DDPM scheduler that I have discussed in the slide. So with DDPM schedulers, how easily the noise saturates and how the clean image weightage goes is what we see here. So that is the particular thing. So here you can see how the noising works. So there, if you have seen the previous thing, you would have seen that the noise only happens at the last step. But with the DDPM scheduler, it even happens at the third, fourth step, the noise occurs. So this is the basic scheduler that we'll be using, DDPM scheduler. So I'll be showing how this scheduler, with this, how do we train it, the diffusers later, and also the time step conditioning and sampling, as I told, plays a major part in training the diffuser. So basically, these two things we need to be clear on, like what is the modified unit architecture that is being used, and how the scheduler plays a role in training the network. So these two things, if it's clear, I will be going to the next slides. So now I will also tell what are the other the things that are important and then we will be searching how do we train a diffuser model. The first thing is the accelerate. So accelerate is basically a Hugging Face library where it accelerates the training process. So how it does it? It makes it to the distributed configuration. So it distributes the process, and with which it helps in getting very lower training time to get optimized models. So accelerate how we will be using that too. I'll be showing in the code example.
Maybe put it in presentation mode, Gautaman.
Yeah, sure. So diffusers, how do we train it? So as we have seen, sample some random time step, noise the data, feed the noisy data to the model, and compare the model prediction. So as we have seen, so this is the basic step in any diffuser model. So we'll be seeing how this is being integrated with the diffusers library. So another major thing that we need to be knowing about is stable diffusion. So stable diffusion is a variant of the diffusion process and this is where this is what has been become very prominent now. Now we have this high resolution images that we get within seconds, and one of the major breakthroughs that has allowed this is stable diffusion. So stable diffusion, what it does is doesn't work on the pixel images itself. Instead of this pixel images, what it does it creates a compressed version, the latent space, and in that latent space, it tries to work. So that is the major difference between the diffusion and the stable diffusion. Uh, so here we have this input text, which is this paradise cosmic beach. We have this text encoder, which is the clip text. I'll be telling about clip text in next things also. So there we have the token embeddings, and with this token embeddings, we have this unit plus scheduler. We have this processed image application, and from this the decoder. So here up to this process, it may look like a normal diffusion, but here this image decoder is what is this stable diffusion is all about. Here, it no longer works on this pixel space; it works on another latent space, and from this latent space, it brings back to the pixel space with the help of this image decoder. So that is what the major difference with the normal diffusion process.
No, can you repeat that, Gautaman? So earlier in UNet it was image to image. Now it
Yes.
is text to image. So what? How exactly it went from being image to image to text to image again?
Text to image is essentially like even in diffusion we can make it text to image. So that is so that how we do is essentially we take the text and we sample the point and we'll be able to get it. So even in diffusion process we can do it with text. So that remains the same. Here, what is the major difference is this image decoder. So why this image decoder is being used is whatever this image information created, right? The unit and scheduler, whatever we have seen up to now works on the image space. The MNES digit, for example, we take assess the image and we try to denoise it. So here, the stable diffusion, what happens is, let's take for example, this MNES digit is in some space. We try to for example, make it as 28 cross 28. Now this goes into another latent space where it's, let's take for that as 4 cross 4. So this 4 cross 4 is what goes into this unit plus scheduler. So it's no longer on the image pixel scale. It goes into that latent space. That latent space would give us an output, and we would have trained a encoder decoder for mapping this pixel to latent space. So we use that decoder to get back to the pixel image. So that's what is the major difference here. Hope it's clear.
Yeah.
We'll be also seeing in the upcoming slides also how it is different. So here, this is what the stable diffusion process is all about. So here you can see that. So this is the X is the pixel space that we are talking about, and we have this auto encoder contracting part, with which it goes into this Z, which is the latent space. So this is the latent. This whole thing is the latent space. So instead of working in the pixel space, it goes into this latent space, and in this latent space, the diffusion process happens, where the forward diffusion, as we know it happens to get this ZT. So once we have this noised image, we get this. We try to make the reverse diffusion process, where we have the noise and we try to get back to the original denoised, not image actually. This is the latent space. So this is the process here. Here you can see that the text conditioning is how it is being done is with the help of this, where we can condition it on anything that we like. For example, the semantic map. For example, let's take where we just give a segmentation image and we want to create an image. So one example I could think of is like we just draw some trees and we input that, and it will actually create an image with those trees, real image. So that things works with the semantic map, where we condition it on semantic maps to get the original image. Text is what we have seen a lot, where we give a prompt, and with that prompt, image is being generated. So these kind of conditioning that we need to be doing. So that is being sent here, and noise with that conditioning is being added with the attention network, and with that we attention network, and with that we get the denoise sample, and from so this again the latent space. So this encoder decoder architecture helps us to bring back the latent space into the pixel space. So this is essentially how the stable diffusion works.
Sorry, I didn't understand. What is the difference between latent space and pixel space?
Pixel space is a different space altogether. For example, just an image is like 28 cross 28. So that is in the pixel space. We use a auto encoder to create into a different space where the same image will be represented by 4 cross 4. Now this latent space you can't like output as image, because it's no longer in the pixel space. It's in another space, but that can be used for the diffusion process. So why do we use it? Is pixel space is a huge thing, right? Like we have this high resolution, and that would make it very tough to train images. So we try to move this pixel space into this latent space, by which the training becomes a lot easier.
So would it be correct to say, Gautama, latent space is a lower dimensional embedding space?
Yeah.
So it is dimensionality reduction, huh?
Yes.
Just like we do text embeddings, we are doing image embeddings.
Mm-hmm.
Okay. Got it.
Okay.
So this is about the stable diffusion. Again, that same thing that I've told, where like you have the original image, you have the image encoder, you have this compressed image, which works in the lower dimensions, and with that we add the noise at different time steps. Again, we denoise it at those same latent space, and with the decoder we try to bring back the original image. So that's how the latent space works.
There are some questions on chat, maybe this around this cosmic beach and few others before that.
Okay. Yeah, Paradise Cosmic Beach. So let's take, for example, that Paradise Cosmic Beach. how it outputs a particular images. Essentially, it first needs to know that it is a beach. So that is being done through this conditioning process. So with this conditioning, it will understand how this paradise beach should be created. And the next question that you have asked is how that particular image has been created. How it will know the beach could be in different ways, right? How that particular image is being created. That is just a probability. Like even if you give a prompt and generate an image, and again you enter the same prompt, the beach would be a completely different image. So it's just a probability. Even for the same prompt, you would get different images because it's sampling from that distribution to create the image.
So if you want repeatability, you cannot achieve it.
No.
Same image if you want the second time, and if you want to try in Midjourney or anywhere. So
I think kind of that random generator, that seed kind of concept is that I haven't tried. Probably with that we could create.
No, I think by tightening the control logic, you could generate almost similar image. So because we want it to be creative, right? So it's creativity versus exact replication. So here we are giving it some loose rope by letting it slightly creative. But if we want a more closer to original image, we can tighten the control logic so it will create almost nearly same image, right? So because that's in our mathematical control, how much leash we give it to be creative, right? Same in prompt engineering in LLM. Do you want it to be uncreative, give very precise answer, or you want the LLM to be slightly creative? Same exact logic here. Correct, Gautam?
Yeah, like the exact repeatability would be a problem because
because it's
won't.
just an English sentence, right? So I mean, how will it know what I am imagining?
I didn't understand.
No, I mean, how would I give in an English sentence that you prepare this kind of, suppose you're making a beach. So you make this beach with these trees. So it won't understand that what was, I mean, unless it knows what was the previous image and this image. To repeat it, I think it requires some kind of, so it has to know what was the previous image and then only it can repeat, right?
No. Like Paradise Cosmic Beach, even at the first attempt it will do. The second attempt also it will do. The thing is, it samples from that distribution, that space. It could be two different points, and it would be two different images. Again, both will be beaches, but both will be different. But to get that exact repeatability, I don't think so. You could create that.
Okay.
Even with LLM, LLM is also a probability output, right? Large language model ChatGPT. I have noticed that if I give the same prompt, it is able to create pretty close same output, generative text. So I think the generated image can be very close to it if the prompt is same. But again, it depends on those control parameters in the mathematical equations. So while it may not be very precisely same as, but it could be very close to it. Even in LLM, I have noticed that it is able to create pretty much the same exact answer, actually. Very close
like
to it.
if you make the prompt more and more specific, it will be very.
Yeah, there is also prompt engineering here also. Just like in ChatGPT, you have prompt engineering. Here also there is prompt engineering, right? The input text prompt needs some engineering. You can specify, make sure the beach has only blue water, not sand mixed with water. There shouldn't be any obstruction. There shouldn't be any board. You can give very long form prompts, and that it will follow your command. So it's a very command and control structure based on how you formulate the prompt, just like in ChatGPT.
Okay. But if I want to create a movie kind of thing, but I want the repeatability, right? That I cannot achieve it. That's what.
No, in that way you could create that image to video, right? So that will be the same.
Okay.
Let's say you want to create Shah Rukh Khan, imagery, right? So you can get to it actually. So you can get to it where you create a pretty good replica of Shah Rukh Khan again and again and again, or Amitabh Bachchan for that matter. So yeah, I mean, again, there's a lot of control logic happening in the maths. So it is totally based on how you set up those mathematical, vector multiplications.
Okay. Okay.
So the latent space we saw, the reverse diffusion, again, just a illustration of how it works. So here we see the noise predictor. How much is the noise? So the objective of what the unit needs to find, whether just the denoised image or the amount of noise, is something that we could explicitly control, but they have found that finding the noise and just subtracting that from the actual noisy image is something that's proved to be good in creating these reverse diffusion. So that's why they are just predicting what is the noise, and that they are subtracting from the image to get the denoising. Again, that they are sending to the noise predictor to find the noise, and that they are subtracting from this image to get the image. So that's how the reverse diffusion works. So other important thing is the guidance. So I think something similar to temperature in LLMs, where we want what is the exact thing to the creative. So that kind of the scaling that we need, that could be adjusted with the guidance scale, both in the diffusion process. Now also I'll be showing the code sample where we can actually add losses with which we can guide the model to go in a particular direction. So here if you see, this is like particular color loss I have added so that the images generated would have a particular color. And here we have this clip loss where we fine tune it to the particular prompts so that it will move towards this images that looks like this paintings of a particular prompt. So guidance is also something that we'll be seeing in the code too. I'll be showing how the training works. So the first thing is we install the libraries and we log into the Hugging Face. So why do we log into the Hugging Faces? Hugging Face gives option to upload our model. Just like a Git repo, we can upload our model, and from there we can directly import the models for a future inference. So that's why we are just logging into the Hugging Face, and then we are trying to show some images in the grid structure. So here if you see, so we saw about the stable diffusion, right? So from diffusers we can import that, and we can load that particular stable diffusion pipeline from any of the models. So here there is a Dream Booth model, particularly trained on this images of this potato head. So we can use that as the model and load the pipeline and give a prompt on how we need to be doing. Like here, particularly this, we need this potato head to be like an oil painting to be drawn somewhat like a Picasso. So once we give this, it will try to generate those images. So that's how the stable diffusion works. And there are other things too here, like for example, when we fine tune on a particular set of images, we use this token SKF. So that is why it is being used here. The number of inference steps, so the sampling process that we saw, how much times it needs to be repeated, so that we can be giving, and the guidance scale. So the guidance scale would determine how exact or how artistic it should go. The default parameter is 7.5, so that is being kept in generating this image. So this is how the stable diffusion works. So we'll be also seeing the diffusers three main things, which is what is the diffuser pipeline, what is the diffuser model, and the diffuser scheduler, and how do we train a model. So how do we train a model? The first thing is like we'll be trying to train a set of butterfly images. So how do we create those? How do we train that? Is what we'll be seeing here. So here we can see that from diffusers we are having this pipeline, DDPM pipeline, and from this we are creating these images. So here you can see from the data set we have these images. So how do we create? So here we are directly seeing from this particular checkpoint we create those images. So here we are using a very small pixel space with less epochs. So that's why the images are this type. So as we use more and more images, more bigger pixel space, more GPUs, we'll be able to get high resolution images. So we'll be seeing how do we create these butterfly images. For that, first what we do is we load the data set. So we have this Smithsonian butterflies subset. We use that as the data set. So the image size is 32. So 32 cross 32 is the pixel size of the images that we are going to train. We are specifying the batch size. What are the different transforms that is to be made? That also we specify. And we have this train data loader with which we load the data and we see the clean images, how it looks like. So here you can see the different butterfly images that we have. The next thing is, so once we have the data being loaded, the second thing is the scheduler. So the scheduler that we saw, the DDPM scheduler, so we'll be using that particular scheduler. So from diffusers, we initiate that scheduler and what is the noise scheduler. So we tell that how much the sampling process, the number of steps to be taken, that is 1000. So we specify that too. So we can see that. So we just see. So now we have defined the noise scheduler. So with that noise scheduler, how the noise image looks like. So that we can just see for our understanding. So here you can see the clean image. So as more and more noise is being added with the help of the DDPM scheduler, you can see it's completely noise image. So here they are discussing about the unit architecture. They're defining the unit architecture and they are taking the training loop. So the training loop, they are specifying the noise scheduler that we have seen. What is the training loop? So they are specifying a epoch of 30. They are just taking the data from the train and adding noise to the DDPM scheduler. They are sampling a random time step. So instead of each as a singular time step, they are just randomly selecting some time steps, and with that time steps, they are adding that for that time step, what would be the noise. So that they are adding to the clean images to get the noisy images. And that noisy images with the time step conditioning they are using in the unit model to get the noise prediction. So this noise prediction is being used to calculate the logs and update the model, the basic unit model that we created. So we can see the loss has been getting reduced as the epochs goes higher and higher. We try to plot those losses. You can see that it's getting stabilized. Yeah. So okay. So now we have trained this model for this butterfly data set. So how do we use that with the diffuser pipeliner? We import the DDPM pipeline and we specify the unit to be the model that we have trained it on, and the scheduler to be the noise, the DDPM noise scheduler that we have initialized. So we have this image pipeline. So with this image pipeline, we initialize and try to sample a random image. So we can see that our model has trained to generate those images. And what we can also do is locally we can save the pipeline with this save train, where it will create this folder with which it will specify the model structure and what is the scheduler, what is its configuration, and the unit architecture. So basically, the unit architecture will have the model weights and also the model configuration details. So all these things will be stored in the local. We can use this pipeline again to reinitialize and generate our images. So writing a sampling process. Okay, here what they're doing is just they're taking some 8 random points and they're using that to generate images. So here you can see with that 8 different random points, we get different butterfly images. So that is how the model is being trained. The other thing that we can do is now we have saved the model locally. Now if we need to directly integrate to the diffusers Hugging Face, what we can do is we can specify what is the name to be given for the model, and we fetch the ID for our hub, and with that we can be creating uploading our pipeline. So this is the pipeline. So in the pipeline we had scheduler, unit, what is the model index, so everything we be having. So for this particular hub ID, so we need to be creating a Hugging Face account, and with which we can be uploading our path there. So here, this is the model card is something similar to README in GitHub, where we specify what is the different things it is being used there, and how to use that particular pipeline. So that we can be specifying and push it. So I can also show how it is being done. So here, so this is my Hugging Face library. So here I have pushed my training code. So here you can see that how to use that that is being specified with the model card, and we have all our models. So what is the different things that is being needed? So what is the schedule configuration I have specified? What is the model weight? So all those configurations that we have, we need that is being loaded here. So that's how we push it to the Hugging Face library. Scaling up with Accelerate is something that, as I told, just to get that better distributed training with the GPUs, we can train it with Accelerate. So that's how, and again, that also they're trying to push it into the code. So this is how we train a diffusers library. Hope it's clear. I can also show about the fine tuning. This is something, fine tuning is also very similar to training, where as fine tuning, we can see about first thing is like a diffuser that has been trained on a different data set being fine tuned on a completely different data set. So let's take, for example, the diffuser has been trained on data A. How do we fine tune to data B? So that is something that we can be seeing. Other thing is the guidance. So the guidance is another thing that also that we can be seeing. Able to run this.
Now, Gautaman, Dreamboat you were talking about, did we mention Dreamboat to the audience?
Dream Booth again is kind of a variation of the stable diffusion.
Yeah, so Dream Booth is a conditioning mechanism, right? So you can, using Dream Booth, you can really create even more, creative images for a variety of situations.
Yeah. The stable diffusion is a model architecture that is being used, but different organizations make their own stable diffusion ideas. So one such as the Dream Booth, the another such as this Midjourney. And I think one of them, I think Midjourney is what it specifically works on this painting and cartoon kind of things. So so that particular prompts, this Midjourney would give better results than other things like a DALI or a stable diffusion.
So, folks,
Okay,
this
so
is a pretty big area. I mean, there are so many algos we have to learn slowly, right? So, it's not easy to learn this in one webinar or even one day.
so diffusers fine tuning is very similar to training. I'll just show uh, some particular things where here if you see they have loaded the model for the diffusers for the face data set that they have trained. This Google DDPM celebrity face data set, they have trained this diffusion model. That is what they are outputting. That they are trying to fine tune on this Smithsonian butterflies data set that we have seen in the training process. So they are trying to fine tune on that and see how it looks like. That is the particular thing. Yeah. So, so that they have trained that butterfly dataset fine tuning and try to see how it looks like. So here you can see that the fine tuning process is underway, where it looks like that from that phase dataset they are slowly moving towards this butterfly dataset. So that's how it looks like this fine tuning process. The important thing is like the guidance metric that we can be using. For example, here if you see the color loss they have used, for the color loss, what it is like the what is the output image that they are trying to with the target, which is just the color. So that they try to use that as the color loss and optimize it. So once they do that, that particular this greenish color is how the images looks like. So in this way, we can have this custom loss functions to guide our images to a particular direction. So another thing is this clip guidance. So one of the questions, if you guys remember at the beginning, that was asked is like I give a prompt and train an image. So how do I know that it is being done correctly? So there, the first thing is the text conditioning that we saw. With that text conditioning, we'll be able to make the generation understand that semantically the different objects how it needs to be placed. So that how do we do that with the clip guidances? Clip is essentially a model that has been released by the OpenAI, where it understands the relation between the text and images to the contrast to learning. So that particular clip model we are trying to initialize, and that model, with that model we are trying to create this clip loss. So what is the clip loss is, whatever image that is being produced, we try to encode it. Whatever prompt, in which way we need, in which particular direction we want it to go. So that particular prompt, we again encode it. That is this text futures. So that text futures, we encode it into the same bit. And this image futures, we get this input embed. So we encode our image to get the image features. For that images, what is the text thing that we have? So that we have, and this for the prompt, what is the encoding we have? This we try to reduce the distance. So for that, they're particularly using this squared gray circle distance. So essentially, they're trying to align it more to the prompt. So that's what is happening here. So here, if you see with the clip process, they are having this particular thing called red rose, red flower painting. So this is what they are trying to do. And so we are using this clip loss to essentially align it more towards this thing. So we have this thing where we have this butterfly kind of data set, but slowly we are moving towards this red painting kind of data set with the help of this clip guidance. So in this way, we can add some custom loss function to make our images move in a particular direction. That's what fine tuning is mostly.
So Gautaman, what is the difference between using core stable diffusion or Dreamboot techniques versus diffuser fine tuning? I mean, fine tuning is incremental machine learning on stable diffusion core model.
Fine tuning is essentially like the transfer learning that we see in computer vision, something like that.
Got it.
So it's been trained on different data sets. We want it on a different data set.
I mean, would we? But stable diffusion is a general image generator. So why does it need fine tuning? I guess it's similar as LLM fine tuning. We need to customize it to our specific industry data set. So I understand that. Now, would I go for Dreamboot conditioning or would I go for fine tuning?
It just depends on the data, right? Like if the data is very similar, let's take for example, it's been trained on some flower data set. We need a particular specific flower kind of generator. So this fine tuning makes sense because it's around that pixel space. It can easily be fine tuned here, but it's a very completely different data set. We can train it from scratch.
Got it. Understood. So the paradigm is not very different from our LLM RAG versus fine tuning, right? Versus training foundational models. So similar paradigm for image generation techniques like diffusion models, right?
Yeah.
Now in multimodal GPT-4, they are already merging image and text, right? So I think there is a multimodal generative AI coming very fast, where image and text will be interpolated very nicely, correct?
Yeah, I think GPT-4 has now, right? Like DALI 3, they're having.
Correct. They are used DALI 3 to augment the GPT-4 multimodal. That's right. Now, one more question. I was in Bay Area in September, so I was listening to Andrew Ng. Had the fortune of listening to this gentleman. He's a visionary guy. So he's saying that the large image model is next. So we have had large language model. So, but yeah, you please finish this. In the end, I would like to ask you this question. Do you have any perspective?
Yeah, I have completed like.
Okay. So any perspective on, because Andrew Ng was saying in his keynote presentation that we have had this massive language innovation with GPT and ChatGPT. It's called large language model. So he is saying I'm predicting images next. So what does he mean by that? So there, even now we don't have a generalized large image model, right? Like we have generalized large language model. So any of your research suggests an upcoming large image model advent of it or beginning of it?
Large image model, I think it's been like these diffusion models itself, it's catching up to very diverse data set, and with the GPT integration, it's almost like any images that we need to create and any particular different set you can easily create.
So we are almost there with multimodal LLMs. Okay. Okay. Fair enough. Any other? So there were some questions on chat. Maybe you can quickly scan through it if you have any comments on any of them.
Yeah.
A lot of questions actually, which I was trying to answer. But excellent presentation, lot of details.
Yeah. Potato oil painting, can it output the image depending on where the user is from, such as the users and to be different? Again, it's a text conditioning. If we want particularly to be different on their cultural things, it could be conditioned on that. That shouldn't be a problem. Fascinating architecture, what kind of applications it could be monetized for? I think it's basically the image generation is what it has been majorly focused on. So creative image generation, but as now what we could be doing is where we need to be training models where we have less data, the synthetic data generation. So that is some space it would go where the monetization would occur. That is what I'm thinking. Yeah, those are the things.
Check some of the others which came above. If you have any thoughts, comments. But excellent research, Gautaman, and you prepared really extensively on this. So I appreciate that. And we all loved it.
Thanks, Gautam. We got pointers where to look into. Yeah, thanks.
Thanks.
Any final comments or questions, audience? All right. Thanks a lot, Gautaman. Look forward to your future sessions. You always amaze us with your deep content. Thank you very much.